Hello and welcome to this episode of the Operating System Development Series. Today we are going to learn about memory, about RAM memory, and in the second part we'll write some text to the screen, and that's gonna be really cool. You probably know what RAM memory is. It's that thing where stuff gets stored temporarily, and the more RAM you have, the better your computer is. Today we are going to look at RAM memory from a programmer's perspective. In RAM memory there are usually stored two types of information. There is code, which gets executed by the processor, and there is data, which is used by code. This means that when you double click a program on exe, that program gets loaded into memory and then it is executed. All the variables, they are stored in RAM memory. An important thing to know is that memory is indexed linearly, starting from 0. So this means that you can reference memory using a number from 0 to 4 GB, for example. Also in programming, memory is referenced using hexadecimal values. You probably know what hexadecimal numbers are. If you don't, here is a diagram that may help you remember. For example, if you want to reference to address 1 MB, you don't reference to value a million and whatever that is in decimal numbers. But you type 0x100,000, which is a megabyte in hexadecimal. And this is how you write hexadecimal numbers in C or C++. You type 0x and then the number in hexadecimal. You probably know that memory is measured in bytes and it multiplies. For example, kilobytes, megabytes, gigabytes, etc. Some other frequently used words for memory size are a bit, which means a 1 or a 0, a nibble, which is half a byte or 4 bits, a hex digit is a nibble big, a byte, which is 8 bits, a word is 2 bytes or 16 bits, a double word, which is most commonly used as a D word, is 4 bytes long or 32 bits. A quadruple word, which is usually found as a Q word, is 8 bytes in size, which is 64 bits. Another important thing is that a kilobyte is 1024 bytes and not 1000. A megabyte is 1024 kilobytes and not 1000 kilobytes. And so on. Gigabyte is 1024 megabytes, terabyte is 1024 gigabytes, and so on. Another important thing to know is how to look at binary numbers. In a binary number, the leftmost bit is the highest bit, and the rightmost bit is the lowest bit. Bits are counted from lowest to highest, starting from 0. To get a binary number in hexadecimal, you convert each nibble in a hex digit, just like you see on the screen. As an operating system developer, you need to know how memory is mapped on a standard computer. So, on a standard computer there are two types of memory: lower memory, which is the memory below 1 megabyte, and upper memory, which is the memory above 1 megabyte. This separation appeared in the 16-bit era, when computers couldn't have more than 1 megabyte of RAM memory. Back in the 16-bit era, computer memory was limited to 64 kilobytes. To overcome this issue, computer engineers came up with the segment offset addressing scheme. So basically, each segment had 64 kilobytes in size, and every 16 bytes a new segment would start. So this way segments overlapped each other. And what's weird is that there are a few thousand ways to specify the same address. Calculating an address is very easy. Just take the segment, which is a hexadecimal number, add a 0 to the end, and sum the offset. Using this memory addressing scheme could give you a maximum address that was above 1 megabyte. To fix this, when you referenced an address that was too high, it looped back from the beginning. And that's a very easy way to crash a computer. Because today's computers are made for backward compatibility, they still start in 16-bit mode, and the bootloader has to make the switch to 32-bit mode. An important thing to know is that not all memory is available for use. Some memory may be used by the BIOS, some of it may be used by some other devices like the video card and so on. In lower memory, these areas are well known. The upper memory is not standardized, but it's mostly available space. Some regions may be reserved for various hardware, but we will know this information when we get to the memory manager. We'll use the information which is given by GRUB, given by the bootloader. Using that information we'll know which area is free and which one is restricted. Now I'll explain shortly what each of the restricted memory areas are. We'll learn about interrupts later, so I'll skip the interrupt vector table. The BIOS data area contains some information related to the computer. Most of it is obsolete and uninteresting. Some useful information may be, for example, the display mode or the base I/O port for video, but most of it is useless. The operating system boot sector, that's where the first sector of a floppy disk is loaded, for example the first stage of GRUB. The extended BIOS data area is not standardized. It contains some information that is used by the BIOS. The video memory is an important location. We will use it in just a moment. And in this ROM area, some other information may be the video BIOS, some mapped hardware, and also the BIOS. Now we will learn about the screen, how to output text to the screen, and we'll start by creating a Hello World operating system, and it is going to get more and more advanced. Let's go to our source code, to the MyOS folder, the Word directory, and inside the kernel folder I'm going to create a new directory called include. Now let's open a text editor, and I'm going to save a file. Inside the include folder, let's call this file, I'm going to choose all types. I'm going to save it as console.h and press save. Now first we need to make sure that this file wasn't already included, if not defined, if and def. 2 underscores console underscore h and another 2 underscores define console underscore h and endif. Between the define and endif we will write everything we need in this file. Before we continue writing this file we'll need to write another one, so I'm gonna create a new file and I'm gonna save it as types.h. Same as before, make sure it was not already included. We will often need to know how big these data types are. Let's start with char and continue with short, int and long. So type def sign char int 8. Type def unsigned char uint 8. And we're gonna do the same thing with short and so on, with all the other types. Okay, now I'm gonna create another type. This is my preference. You can do it or you can use the default type. I'm going to call the string type, which is char with a star. I'm going to call it string. Create a new type structure with 2 integers, x and y. So create a point and unsigned point types. This is a matter of preference. If you don't want to use these types, you can create 2 variables instead. Okay, now let's go back to console.h. We will need to include types.h. Define here all the functions that we are going to create and define them as extern. So first we will create a function which will clear the screen, console clear. We will also create a function which will output a character to the screen, console write char and char c. also a colored version, and the color will be an unsigned byte. Okay, and let's also write strings to the screen. Console write string and console write string colored. Okay, these are the basic functions we need in order for a console to work. Another thing, we need to know how big the screen is. Maybe later we will have a different text mode, a different size. We will use defines to do that. So define console width, it's going to be 80. Console height will be 25. Now let's create another file called console.c. And I'm going to put it in the root directory in the kernel folder console.c. And I'm going to choose all types. First, let's include console.h. And let's copy all these declarations. We are going to write the implementation in this file, console.c. Now another thing we need to do is have a cursor so that we know where to write every character. So uPoint console cursor, and the default position will be 0 by 0. And we'll also need to know the screen size, console size. Let's use these values that we defined. Console width and console height. Okay, another definition will be the default color. And the default color will be 0x7. This means 7 in hexadecimal. This value stands for black background and light gray foreground. So I'm going to declare another enumeration this time. So enum colors, I have already done this and it's in my clipboard, so I'm going to paste. Okay, so these are all the colors that are exist in text mode. Black, which has a code of 0, blue, green, and so on. The color property is specified through two values. First is the background and then the foreground. The background is the high nibble and the foreground is the low nibble. So basically this is how a color would look like. For example, you need black background and white foreground, 0x, 0f. If you want a blue background and a brown foreground, you would type 0x116. So this is how you specify colors in this text mode. Now let's go and implement the console clear and console write functions. Okay, first of all, console clear. I'm going to remove the external keyword for every one of these. Now let's start with console clear. We'll need to declare first another variable. This time it's going to be an unsigned byte. And let's call this video RAM. Now to output text to the screen, you need to write to an address, more specifically the address B80000. So this is going to be a byte pointer equals, and I'm going to cast the address 0xB8000. This is the address we need to write to. Every character you see on the screen is represented by 2 bytes. The first byte is the ASCII code for the character and the second one is the color. So basically you would have 80 multiplied by 25 multiplied by 2. That's the total bytes that the video RAM has. This is exactly what we need to do to clear the screen. Empty all these bytes. So let's create a new variable called I, which is going to be the counter, and for I equals 0, I smaller than console size dot x multiplied by console size dot y multiplied by 2 I++ and video RAM of I, and we are going to write 0. Next we need to write the character. We will use the colored function to do that, so console write char colored, and the character will be C, and we will use console default color. And if the color is specified, this is where we need to calculate well we will write the character. Let's create a new unsigned integer called location equals, and this is how we calculate the address. First we need the x position plus the y position, so multiplied by the console width, console size dot x. Now we write the character to that location, so video RAM of, now we need to write 2 times location because there are 2 bytes for every character, equals the character, and video RAM of 2 times location plus 1 equals color. The next step we need to do is to increase the cursor position, console cursor dot x++, and now verify that we don't try to write after the line has finished. So if console cursor dot x is bigger than or equal to console size dot x, console cursor dot x equals 0, and skip to a new line dot y++. Now for the console write string function, we just call the colored version, so console write string colored s and default color, console default color. This is what we need to do. We need to write every character in the S until we find a 0. So while star S, this means the character contained in the S pointer, because it's actually a char pointer, while S different than 0, console write char colored, so write the character S and using color. And next we need to increase the S pointer, S equals S plus 1. Now let's go back to the main function and let's include console.h. Now we are ready to output the first text to the screen, so let's call console clear first, clear the screen, and console write string hello world. And in fact, let's make it a little bit nicer and make it colored. Let's write it to color light magenta, because we didn't specify any background. This means that it's going to be 0, so black. Okay, now we need to go back to the build.sh file and add console.c. Okay, so now I'm going to come to the compiler and I'm going to cut all these parameters except for output and input file, and create a new variable called OPT. This means options, and it's going to stand for compiler options, and I'm gonna put every single option except for the output file and input file. And now append OPT to the compiler parameters. Now let's copy and paste this line and replace main.o to console.o and main.c to console.c. Now we can launch Cygwin and build this kernel. Okay, now I think I did something wrong. Make sure you have the right file opened in Cygwin. You may have to start a driver. Okay, I'm going to select my OS as the opened file, and now we'll rebuild it. Now open VirtualBox and let's test our kernel. Open the testbed machine, under devices, floppy devices, make sure host drive A is selected, and there you go. So congratulations, you have successfully created your first Hello World operating system. We will continue working on the console in the next episode when we will implement scrolling and other important features of the console. So see you in the next episode.